welcome back to the second part of solving optimization problems with neural network constraints. So the problem that I've been studying or we've been looking at is an optimization problem that has embedded in itself a trained neural network. So a neural network that gives us a response of a quantity of interest that we're interested in, given some input variables x over which we're now optimizing. And these problems, these class of problems, are becoming more and more prevalent because we can often model complex physical phenomena with a neural network at a cost that is much, much lower than running an expensive simulation. And we saw in the last lecture that one of the caveats here is that deep neural networks, when they have ReLU activation functions, these nested maximum of piecewise linear functions, then optimization solvers really suffer. So optimization solvers that are built for problems with smooth, continuously differentiable or twice continuously differentiable functions, they no longer work because the functions that we now get when we plug the D and N with a ReLU activation function in there are no longer smooth. And as a result, you see slow convergence or non-convergence of these methods. And we saw this example where IPOP took 3,000 iterations, but when we swapped out the activation function, it suddenly went and solved the problem in under 30 iterations, so 100 times faster. Okay, so what I want to do in this lecture is talk about formulating these problems using integer variables, and then I'll give you a second alternative formulation. So this is the problem that we're studying. The functions, the original functions f and g are smooth and maybe twice continuously differentiable. There may be some additional constraints. There could be integrality restrictions, for example, on some of the variables. And in my case, the one example that I showed you, the compression ratio is an integer variable, for example. And DNN here is a machine learning surrogate. So the first trick we're going to use is a trick that you're now familiar with. We've used this in the constraint disaggregation. We've used it when we're rewriting optimization problems. When we look at the computational graph, we introduce additional variables and disentangle these nonlinearities. So here, what I did was just introduce a variable YL, which is the prediction that comes from my neural network, and just treat this as a slack variable, for example, and replace my neural network inside my nonlinear functions by this new variable. And immediately there's a benefit, because if the original functions were convex, then these new functions are now also convex. So I have this benefit that the function that I have up here is most likely not convex in X, but when I do the substitutions, now I have a convex function for my objective and my constraints potentially, but I still have a non-convex constraint. But I've now isolated the difficulties in a separate part. And so that's also a general theme of what we've been doing in this class. So once I've done that, then there's a second trick that I'm going to use, and I'm just going to rewrite my max function using binary variables. And that's also a well-known trick. You've probably seen this before. So in particular, I'm going to introduce two sets of variables, slacks and binary variables. So the slacks are blue, this S, and there's one binary variable. And I have one binary variable per max function that I'm operating on here. And then I can rewrite, what I do is I rewrite my function here in terms of the slack variable, and I can quickly check that this formulation is correct. So m is a positive, large positive constant, and if z is equal to 0, then y is equal to w, then s is 0, y is equal to w transposed x plus b, and y is non-negative. So for z equals to 0 or z equals to 0, we're on this part of our max function. And if z is equal to 1, then I'm in fact on this part of the max function. I can quickly check that. If z is equal to 1, then y is equal to 0. and now minus S is W transpose X or plus B, or S is minus W transpose X minus B. S is non-negative, so that means that what I have here is in fact negative or non-positive. And so this formulation is exact, this reformulation. And what I now get is, I now have a problem. If I put all this together into my original problem, I took out the part with the ReLU functions, and I now have this system that's effectively a linear system of inequalities. So this is a polyhedral set with some binary variables and some additional slack variables. And if my original problem was convex, then I now have a convex mixed integer nonlinear optimization problem. So that's a very favorable and nice property. And this just follows immediately from all the results we've seen before of convexity of these nonlinear functions and the linearity of the mixed integer optimization set. Okay, so this seems like it's doing great. There's some caveats here, and one is that I need to get, ideally I want to get tight upper bounds, these M variables that I have here, and I can potentially get them by doing bound tightening techniques, similar to the optimality bound tightening techniques that we discussed a few lectures ago. I can apply them to get good tight upper bounds on M. But that in itself is actually not enough, and there's been a nice paper by Joey Anderson and some colleagues that give a stronger mixed integer optimization formulation, where they actually find the convex hull of this mixed integer feasible set that I had on the previous slide. So they find the convex hull of this mixed integer set. And this is actually quite hard to do, but in doing so, once we find the convex hull, then we're guaranteed that if we optimize linear functions over this convex hull, we will find solutions that satisfy the constraints. The convex hull is actually quite hard to find. It's exponential in the size of this max function, or the dimension of the max function, but they have efficient separation routines. So what you can do is you can use that as a cut generation approach when you're solving this mixed integer nonlinear optimization subproblem to generate cuts that separate points that are not in the convex hull from points that are in the convex hull. So we then have two kinds of cuts that we can add: the traditional outer approximation cuts that we looked at, and these new cuts that we could use. Okay, so we coded this up, or Dominic coded this up, we ran it, and we solved global warming. I have great news for you. We could design an engine that actually sucked CO2 out of the atmosphere. Of course, that's total nonsense. That engine doesn't exist. What was happening was, in fact, that we had our training data that was each of these red dots corresponds to a training point. So the training data is very, very, very dense. There's a lot of training data. The optimization solver was converging to this point down here. So those are my iterates. So I have absolutely no knowledge really about this function outside of the set of where I have the training data. And as a consequence, I'm just predicting complete garbage. And in this case, I was predicting that my new machine would solve global warming. You can also see on these lines here you can see the training data. So each of those is a trajectory that we trained on, and they're overlaid in red. And in blue are the points that we generated that are outside the hull of these training data. So they really clearly make no sense in terms of replicating the true behavior of this engine at all. Okay, but we can fix this problem and by simply finding the convex hull of the training data. So if you look back at this picture, it's not hard to find the convex hull of the red points, and then we would simply restrict ourselves to lie inside the convex hull of the training data. If it's not possible to find the convex hull, then you probably have to go back and retrain your neural network if you find that you're getting non-physical solutions such as these here. But that's not something that we considered in this example. And so once we force ourselves to stay inside the convex hull, we find solutions that are sort of also within the convex hull of the training data, but that give us slightly different compression ratios. So we simulated for these 5 different compression ratios, and here we're sort of selecting a different one, which is an indication that we're finding interesting solutions to the optimization problem. But we're not solving global warming anymore, so that's the downside. There's other solutions to that. Solving these problems is really, really hard, and so we were using CPLEX to solve the mixed integer optimization formulations for this engine design problems. It really quickly ran out of time. We had an upper time limit, I think, of 3 hours. And so if we just had a single layer, so a very simple neural network with just a single layer, we could go up to maybe 100 or so time steps. But for smaller problems, we could only do a very small number of time steps until we ran out of steam, just because the MIPS were too large. And this was largely due to the big M formulation. We didn't try the new formulation, the separating those cuts. That might have helped in this case. So then the question is, okay, now I've shown you this example of using binary variables or integer variables to remodel these ReLU activation functions, but it doesn't seem to work for very large neural networks. So what do I do instead? So one approach would be to use better cutting planes. Another might be to use some of the heuristics. What we did was we actually went back and tried a different nonlinear formulation. And so we went back to this maximum function, and we formulated it as a complementarity constraint. And so I haven't taught about complementarity constraints, but we've seen the KKT conditions, and these complementarity constraints arise in the KKT conditions. So I can model my max function as saying either y is equal to 0, so I'm either here, or y is equal to w transposed x plus b, and I'm on this branch here. And this is how you interpret this notation here, that you're either on one branch or on the other branch. In other words, either y is equal to 0 or y is equal to this residual. And then the inequalities will ensure that you're not generating points that are not feasible. And so in addition to this disjunction, you also have these 2 inequalities. And this complementarity constraint, for example, arose when we were looking at Lagrange multipliers for our nonlinear optimization problem. Either the constraint is active, in which case the multiplier can be positive, or if the constraint is inactive, then the multiplier must be 0. So you can think of this y as sort of being your multiplier, and the right-hand side here as being your constraint. And then that's something that you've seen before. Okay, so how do I model these complementarity constraints? There's, again, a simple trick. And this works really well in practice. You introduce slack variables as before. And by introducing these slack variables and having one linear equation, I can now model the disjunction here with one nonlinear inequality. So I have a non-negative slack, and then this nonlinear inequality means that either a component yi is positive or a component si is positive. But they can't both be positive because the sum over all yi times si has to be less than or equal to 0. And it's important for numerical reasons not to write equal to 0 here. So typically when you see complementarity constraints, you see them written as equal to 0, but that gives rise to some undesired properties numerically. Still, this formulation violates constraint qualifications. So for the nonlinear solvers, you need to be a little bit careful, but there's been a lot of progress on making sure that the nonlinear solvers work for these kind of problems. And so Nitro, for example, has a feature that allows it to solve problems of this type by taking a penalty function approach. We take a slightly different approach, and we can still show fast convergence under certain circumstances. So this is even though it violates a constraint qualification, this is quite a mild violation of the constraint qualification. It's very structured, and you can take advantage of the structure when you're solving these problems numerically. Okay, so then I end up with this tractable non-convex nonlinear optimization problem where I have my original objective function and constraints. Then I have the representation of my neural network, and I now model the disjunction that I modeled previously with my binary variable. I now model it with this complementarity constraint here that ensures that only one side of these two inequalities is positive at most at any given time. And you can make some nice statements. You can show that first order conditions of the two problems are equivalent in a certain sense. This problem is much nicer because it's actually a smooth problem. So we no longer have the non-smoothness of the neural network constraint here. We sort of handled this by explicitly modeling the max function using the disjunction. And we can solve this with large-scale solvers. So I just have some little results, and I'm not going to go into too much detail here. On the x-axis are the number of time steps. So we want to get as large a number of time steps as possible, ideally to 1500. We have three different solvers. So the MIP solvers are in blue. They're running out of time basically for anything above 50 time steps or so. The nonlinear solvers, the nonlinear non-smooth solvers that I showed in the last lecture are in green, and these MPCC or complementarity-based solvers are in red. And so what should you take away from it? The complementarity-based solvers work best, and the question then is, do they get good solutions? And the answer is they get reasonable solutions. So they may be having a larger optimality gap than the MIP solvers on some of the smaller problems, but for the larger problems, the MIP solvers don't get a good optimality gap. So this is the gap between what we know of a lower bound and the upper bound that we're computing here, or an estimate of that. Okay, one of the things that was important is finding good initial feasible points. So we worked a little bit on that. And this is sort of the second example is looking at adversarial networks with NLP formulation. I'm not going to go through the details here. I wanted to just show you some results. And this is just one example out of 100 runs that Dominic did after 1 hour CPU time. So you see the training data here of the 10 digits, the MIP solution in the middle, and the nonlinear optimization solution that we get on the right. And so one of the advantages is that the MIP solution that we get, because the MIP isn't solving to optimality, it looks a lot worse, and we're getting really good nonlinear programming solutions. So this is the solution that it will be, every single digit here will be misclassified. So we ask the optimization problem to classify basically the 0 as a 5, the 1 as a 6, 2 as 7, 3 as 8, 4 as 9, and then cycle back. So this is a complete misclassification problem, and you can see that by just adding a little bit of smudge around the numbers, you misclassify all of them in this case. Okay, so I've looked at this optimization with deep neural networks, and the takeaway message is that if you're modeling these problems, then you can take advantage of the PyTorch and TensorFlow technology for computing gradients, but you do that at the expense of possibly making the problem really non-smooth, and non-smooth in such a way that the nonlinear solvers will not work. So then it's important to think about reformulations. And so there are three optimization formulations. The embedded formulation is the one that's non-smooth, that directly uses PyTorch or the optimizations or TensorFlow and its automatic differentiation. You can reformulate the ReLU function as a mixed integer optimization problem, and that works well for relatively small networks. And you can potentially solve them to global optimality. It's much more efficient to formulate them as complementarity constraints. And one thing we haven't tried here is to think about ways of combining these two. And that's maybe also an open question, where you generate smaller MIPs. If you do the mixed integer optimization formulation, then I think it's also important to generate cuts, efficient cuts for these ReLU function reformulation. And really this is just the first step towards doing some form of rigorous optimization over machine learning surrogates. And there's a lot more work to be done. In particular, as you saw when I had the one example where the optimizer was wandering off and finding points that hadn't been trained on before, you may have to have this inside a loop that actually retrains the neural network. So the assumption that the neural network is there and given forever is not necessarily a realistic assumption. And so there's lots of things that one can still do. One big problem with neural networks, with large language models, or any machine learning tool is that they're not necessarily good at predicting outside of the training data. And so in my case, I had very, very dense training data. If you remember that picture, we had this area, and it was almost densely covered with training points. So of course, that's a good predictor. But if you want to explore regions outside of the training data, then you need to do something else. And in particular, retraining neural networks is one thing. There's some interesting papers recently by these authors here who were looking at adding an optimization layer to your neural network. So you actually train the neural network to find an optimal solution, and the layer that you're adding is essentially the first order conditions of the optimization problem that you want to solve. So you can add these first order conditions and then somehow learn optimal solutions. There's a big issue in terms of how to overcome the scalability issues if we do these reformulations. So if you think about large language models, they have billions or maybe trillions of parameters soon. And for those, it would simply be prohibitive to add a binary variable for each of those little neurons that you have. So we need to find ways of making these algorithms more scalable and maybe finding ways of doing integer programming at scale there. And then there's questions about convexity convergence of solvers that are quite challenging. And overall, it's really quite cool because you're dealing with non-convex functions. You can often plot these functions much easier because you can explore these neural networks very easily. But expanding them and making them into a tool that is predictive for science, where you can also verify and validate the solution, that's still an open question very much. And something that we're working on at Argonne, for example.
These deep neural networks, anyway, they solve some optimization problem by default. They fine-tune those parameters.
Right. So to tune the parameters, you have to solve an optimization problem, the training problem. Which ones did you mean? The I don't know. I think those are interesting questions. I think now some of this may need to be cut out because I'm not sure I'm allowed to say this, but it's not clear to me that going to 1 trillion parameters is necessarily where we want to be. It's not clear to me that we have the technology yet sorted out for the activation functions, for example, the very simple activation functions. And we make this connection to neurons in the brain, but the neurons in our brain are more complicated functions than these simple functions that we have here. And so there's probably scope for having other forms of activation functions, other forms of computer architectures on which to run this. So it's not, at the moment, it's not clear to me that we're running this, we're having neural networks that look the same in maybe 10 years' time or so. I think there's a lot of new hardware architecture that's coming along that may be better suited to doing some of these training tasks, some of these learning tasks. So there's people looking at quantum neural networks or quantum machine learning. There's neuromorphic computing. So there are different, much more esoteric computer architecture that have maybe a better chance of mimicking what we're trying to do here. And the traditional architecture that works with bits is maybe not the best suited for doing the learning and the training tasks and the sort of inference that we want to do afterwards. But that's just me speculating. I think there's some effort going into finding out what the best architectures are. Yeah? Parallelization. So in order to address the scalability issue, you mean? Yeah, that's probably a good idea. I think at some point we will need that. There have been some efforts, we didn't talk about it much in terms of parallel branch and bound or branch and cut. They have themselves scalability issues in the sense that they don't scale to very large machines. So they don't scale to the biggest machines that we have. And again, it's a question maybe of not having the right paradigms yet for doing a parallel branch and cut tree search. But that would help. That would certainly be one aspect that would help. And the training, when you're training these neural networks, you're training them on high performance compute platforms. So we're building neural networks for science on sort of the leading edge compute platforms that we have at Argonne, for example. And that's all done in parallel. So the training is done in parallel. And the integer optimization could also be done in parallel to some extent, but it's challenging. That's certainly a challenge. Yes? Correct, yeah. Yeah, so I sort of brushed over that a little bit. The formulation that I showed was there. It was for one neuron. Yeah, but I would, so I need a binary variable for every neuron. And that's what makes this expensive. So on the next slide, so if you burn this into the back of your retina, you will see it again on the next slide. It's back here. But now my binary variables are indexed. They now are vectors. You have to think of those as vectors of variables at every level of my neural network. I have a vector of variables, and I have one variable per neuron in my neural network. And that's quite expensive. I think if you can sparsify your neural network when you train it, that might help, because then we have fewer integer variables. And that would certainly help this approach. And then the cuts are really just for a single, each one of those, a single one, there's cuts. And the cuts, an exponential number of these cuts, which makes it hard to write them all down, but we can separate efficiently. That's good.